Welcome, everyone, to Astronomy on Tap Copenhagen, our second Astronomy on... Oh, whoops, I should unmute myself. Welcome, everyone, to Astronomy on Tap Copenhagen, our second online Astronomy on Tap event. So we hope that everyone is being safe right now, so maybe I'll just change the view so you don't need to see me. So I hope that everyone is doing safe during the lockdown. So because it's our second time running the event, we are able to bring back the quiz. We had a lot of people who were very keen for the quiz. So we'll hear from Nikki, who is our helper here today. We also have Jurgi, who will be looking at the questions in the chat. So please, while we have the talks going, you should type your questions in there and we'll ask them during questions time. And of course, we have our speakers for this month, Sophie and Alejandro. So they're very excited to talk to you. So this month's theme is blazing binaries, because 5 years ago was the announcement of the discovery of gravitational waves. I don't know if you remember where you were, but I have a tiny little video of exactly where I was. If I can pull it up. Okay, hold on. I was at a conference in Melbourne, an astrophysics conference, and it was 1 a.m. and maybe the audio isn't coming through, but there was me. We were trying to mimic the sounds of gravitational waves, and there was Katie Mack. So we were all pretty delirious because it was 1 a.m. and it was just a very fun experience. And since then, in the last 5 years, we have discovered a lot of things about gravitational waves, and Sophie will tell us about how we can get to the things that will make them, and Alejandro will teach us more about the actual event itself. So I guess we can start a little bit earlier. So Sophie is a PhD student at DARK NBI, looking at how binary stars can interact and eat each other. So would you like to take it away? So let me just
me share my screen.
Yeah.
Okay. So can you see my cursor? Yeah.
Yep.
I hope so. Okay. Well, yes. Thank you for having me come here today. I'm very excited. And as Reggie said, I am a PhD student. I work at DARK, which is one of the centers at the Niels Bohr Institute, which is basically the big KU physics department. So I am going to be talking about the formation of binaries, and specifically the formation of binary black holes, which are these type of stellar objects that we see creating these gravitational waves that Reggie talked about before. And already in this introduction image, I have a picture taken of a binary star system forming, and this is taken in radio and looks kind of crazy. And it's like this: you have two bright objects, which are the two stars, which is what binary refers to, is that there are two. And basically that's like what this whole talk is going to be about, is how do binary stars evolve. But firstly, binary stars are two stars that are formed really close together, and they're so close that they're like the same distance as the sun and the earth. So the sun, for example, is a single star because there are no other stars close by that is affecting how the sun moves. It's only moving around in the galaxy on its own. But binary stars are so close together that they orbit around each other, which means that they go around in circles, sort of the same way that this Earth is moving around the sun. But for binary stars, they're more equal in mass, so they both go around in circles instead. And then specifically, the type of stars that form black holes are really heavy, and those are the ones I'm going to be focusing on. And they're at least 20 times heavier than our sun, so that's really big. So like I said, my whole presentation is going to be going through what happens from you have two stars formed to ending up with having two black holes, so binary black holes. which, as I said, is what gives gravitational waves. But that's the next presentation. I'm not going to talk about that. I'm only going to focus on the evolution. So a star's life depends very much on its mass. And small stars like our sun go through this phase of burning hydrogen in the core. And when it runs out of hydrogen, it actually becomes really big. It grows into a giant. And then it just sort of sits there. Nothing else happens, and slowly it will just lose the outer layer of gas. It drifts away, and then you're left with the core, which we call a white dwarf. And the core just sits and cools down forever. Like, we don't know what happens to them unless it collides with something. It just sits forever and cools down. Bigger stars that are like medium, that are like 8 to 20 times the mass of our sun, go through more phases of burning. So they go through this phase of first burning hydrogen, the same as a small star, but then once it reaches this phase where it expands and becomes a giant, it actually gets really hot in the core and it can ignite other elements. And it goes through all these phases of burning and ends up creating what we call this onion structure, where you have different layers of elements and it burns it and keeps on burning it until it gets an iron core. At that point, it can't burn anymore, because when you try to fuse iron, which is the burning process, is fusion. When you try to fuse two iron atoms to create energy, you don't get anything out. It actually requires energy to burn iron. So the star is sort of stuck. It's trying to like burn something, but it can't, and then it starts collapsing under its own weight. And then it forms a neutron star, which is a really, really dense material. All the atoms are practically overlapping. And when it does that, it releases a ton of neutrinos, and the neutrinos actually blow off the entire outer layer. And then you're left with just a tiny core, the center, which is this neutron star again. But for stars that are even bigger, so at least 20 times heavier than our sun, but also much bigger than that, we know that that last process of forming a neutron star in the center and releasing all the neutrino energy is actually not enough to blow away the outer layers. The gravity of these stars is so strong that the star collapses under its own weight and forms a black hole. And you might think that, like, okay, a star that's 20 times bigger than our sun has 20 times more hydrogen, so it should live 20 times longer. But that's not what's the case, actually, because the gravity of these bigger stars is so much higher. The fusion process in their core happens a lot faster. So this table here is just showing that a star that's the size of our sun, which is 1 solar mass, so that's 1, lives about 10 billion years. Whereas the stars that we care about are in this range of 30 to 60 solar masses, and they only live like a couple of million years, which is a factor of 100 smaller. So this is really, really like a big difference. And that strong relation in timescales with different masses is going to be important when we look at our binary. So now we're going to focus only on the binary evolution, and we're going to start out here after the formation of the binary. We have these two stars. Star number 1, I'm going to call it star number 1, is a little bit bigger than star number 2. And they go around in these orbits, and they just hang out. And they do that throughout the entire process where they're burning hydrogen, which we call the SAMS, or the zero-age main sequence, which is the longest part of any star's life, is just burning hydrogen. So this was like a couple of million years for these big stars. But then at this point, star number 1 is going to start growing, right? It reaches that phase when it becomes a giant. So what happens when a star becomes a giant is that it runs out of hydrogen to burn in its core. It moves on to burning hydrogen in a shell around the core instead, because now it only has helium in the center, so it has to burn hydrogen in a shell. And when it moves that heating source from the deep center out to like a shell closer to all the outer layers, it starts boiling these outer layers. And really what happens is like when you're boiling pasta and sometimes you forget to turn off the heat, it boils over and you have water everywhere. The same thing happens in the outer layers of the star. It starts boiling really heavily and it gets extremely big. But at the same time, the core condenses more and more and it gets hotter and hotter and hotter. So at some point you ignite helium burning. And then the sort of burning place moves into the center again, and the outer layers are allowed to cool down a bit and contract. So you get a normal star again, but instead of burning hydrogen in the center, it's now burning helium. And these are for these really massive stars that can actually do that transition. But when that process of boiling happens in a binary, you see it starts growing and it grows really big compared to its orbit. And you start having these issues where the gas actually of the star number 1, it doesn't really know where it belongs. The gravity of star number 2 tries to pull at it, and it pulls stronger at it than star number 1 does. So you have a small amount of mass sort of slowly flowing on onto number 2. And that way you're actually moving mass from star number 1 over to star number 2. So star number 2 grows, but you're also removing all this outer layer of star number 1. And you end up just having the core left. So this is now a helium core and a bigger star number 2. But it doesn't prevent star number 1 from continuing all these burning phases. So it goes through all those layers of burning different type of material. It forms the iron core and forms the neutron star. It tries to explode, but it still collapses because it's still way too heavy to withstand its own gravity. And then it forms a black hole. So now we have our first black hole. And when we see this happen, we actually see this happen. This is kind of cool. So this is a picture taken of a stellar system in 2007. And you can see this constellation of 6 stars. And then when we look at that same constellation in 2015, 1 star is missing. So we really think that this was a massive star. It tried to explode. It couldn't do it because it was too heavy, and instead it collapsed and formed a black hole. And now it's done. And we see these, as we call them, disappearing stars, but they're really forming black holes, and the remnant of that, so the black hole is still there, and its gravity is still really strong because the same amount of mass is still present. So when we look at our binary, that means that they're still orbiting each other. It's just like, instead of being a star next to it, there's a point mass that's really heavy moving around next to it as a black hole. Now, the second star, which was less massive, so it was a bit slower at reaching this giant stage, but it will eventually reach it as well. And then it starts expanding. But this time, the mass ratio between these two is actually different. It's star number 2 is considerably larger than star number 1 at this point in mass. So instead of just growing slowly and spilling over, it's going to grow really quickly compared to the orbit. And it just keeps on growing. And star number 1, or the black hole, doesn't know what to do. It's now suddenly engulfed inside star number 2. So when we zoom out, we expect this sort of picture. Star number 2 is really big, and the black hole from star number 1 is moving around inside it. And this is really hard for this black hole because it was moving around in vacuum before, and that's what allowing it to keep its orbit. There's no sort of restriction for it, but suddenly it's moving inside a star. So this is like if you're moving through water, it's kind of easy. But if you're trying to move through honey, it's really hard. So the energy of the orbit from the black hole is taken away. It's losing energy and it's spiraling inward toward the core of star number 2. And that energy is not just lost, it's transferred to the star. And we call all these outer layers of the star the stellar envelope. And this process is something that's called common envelope because suddenly you have a star, you have 2 stars inside 1 envelope. So we call this a common envelope. And I have a movie of this setup because it's a pretty complicated process, right? So here is just a simulation where we have tried to explore what actually happens in these setups, what we expect to see, how the gas flows around. And this is a picture of a giant star. And the core of the star is marked here by this little X. And then out here to the right, you can sort of see it is where the black hole of the star number 1 is marked. And then with it, if I start the movie, you will see how it moves in and this gas is flung out. So let's start it. Whee! And you saw this all this gas being flung out and the binaries moving around inside it. It looks really crazy. And they're stirring up all the gas. And I'm just gonna play it again. But you can see all this gas initially is being flung away from the binary. So all this outer layer, the envelope, is being taken away from the binary. And we just left with the black hole from star number 1 and the core of star number 2 moving around inside in this little binary instead. So after this common envelope event, this is our binary. We have the black hole from star number 1 and we have the core of star number 2. And they're now in a much, much smaller binary. But we still have the core, and the same thing as before is going to happen. It's going to go through all the burning phases, and it will form the ion core, it will form the neutron star and try to explode, but fail. It will then collapse, and then you have 2 black holes. So this is the story that we think is the most likely story for how you form binary black holes. This is what's called A in this little catalog, where we saw, okay, we had the 2 stars at first, they go through all this mass transfer events, which is like slowly pulling away, or this very dynamic fast event of spiraling in. But we also believe that there are other ways that you could form binary black holes. And one of them is that if you form the 2 stars in a much smaller orbit from the beginning, so much smaller than the orbit between the Earth and the Sun, that would make the star rotate really fast from the beginning around themselves, so they would spin around themselves while being in the binary. And this actually creates a lot of convection or sort of mixing inside the stars, which prevent them from hitting this giant phase. So instead of going through all this gas and interaction, they just collapse into black holes. Nothing happens along the way. They just keep on staying roughly in the same pattern. And then finally, we have a third way that we think you can form binary black holes, which is through something called globular clusters or stellar clusters, which is when you have a bunch of stars, actually, like 1,000 or 1,000,000 stars formed together. They all interact. And this is a very dynamical process. They just interact with each other, and some of them are flung out of the system, and some of them are flung deeper into the system. And these stars also go through all these processes of burning and collapsing and forms black holes. And eventually, we believe that some of these black holes will be kicked out of the stellar cluster in binaries. So yes, that was the 3 ways that we think you can form binaries, but this is definitely the one that I think is the most likely that we see at the moment. But we look forward to seeing more of the gravitational waves, because the difference that the gravitational waves can actually help us determine which of these models is most likely. And that has to do with what type of spin we expect to see. So like how fast do the black holes turn around themselves? We have slightly different expectations based on these different models. So the more gravitational waves event we have measured, which I think Alejandro will talk more about, the more likely we can pinpoint which of these models is the correct one. And I think, yes, what happens next, that's going to come in the next presentation. So this was all I had, and thank you.
Thank you, Sophie. So if people have questions, you should definitely start putting them in the chat, and Georgi will ask them to Sophie, but we don't see any just yet. So I guess I have some questions. You did point out that a lot of the really massive stars, they can burn out and become black holes in 3 million years, a few million years. It was very interesting thinking about life on Earth, because life has been around for a few billion years. So does it mean there's been like hundreds or thousands of black holes popping in and out of it, like just becoming
within our solar system?
Yeah, not necessarily within our solar system, but I guess just in our galaxy maybe.
Yes.
But I guess the question is like how frequent? How many of these really, really big stars are there that could turn into black holes? I'm guessing they're not always around.
No, there's not a lot of them. So we normally think that there's like one star per galaxy that will, per 100 years, that will form a neutron star, and it's a bit less for black holes. So the rate is really small. We don't expect to see within our lifetime any black holes forming, for example, in our neighborhood, but luckily we can see them very far away. So the picture I showed is from a very different galaxy, so we don't have to see it happen within our own galaxy. But I guess if you say that life continued on Earth for another couple of 100 years, we should definitely expect to see something. That was a very sad note. We definitely expect to see it at some point, but not within the next 100 years.
I don't realize the picture you showed was from a different galaxy, so we haven't seen that within our own galaxy. That's really cool. That could be exciting, I guess. I see that we have some questions coming through. So Georgi, do you want to ask Sophie these questions?
Yeah, so we have 3 questions now, I think. And yeah, so the first one is from Sierra D, and she, I don't know. They ask, Sophie, when did you know you wanted to study astronomy?
I actually didn't know I wanted to study astronomy until I finished my last year of the bachelor. I went on an exchange program, and I had to find someone to work with very quickly. And the nicest person I met while I was there was an astronomy professor, and he was the reason why I decided to do that. He was very inspiring. So, and he worked a lot on these stellar systems, so that's why that's still what I'm working on.
But were you already studying astronomy by the end of your bachelor's, right?
No.
But you,
okay. No. I was studying quantum mechanics, quantum physics. Okay. Yeah.
So now we actually have one more question already. So yeah, the second one is this one. The question is from Crew 19. Is there such a thing as a system with 3 stars, and have we ever observed one?
Yes, there are plenty, and there are also many systems with 4 or 5, not many, but we know that there are systems with 4 and 5 stars also, and we have seen them. That's the short answer. Yes. Actually, the heavier the stars are when they're formed, the more likely they are to be in systems with more and more stars in them. So if you go to stars that are actually the 60 plus solar masses in stars, we expect to be in triples, not just in binaries.
Oh, that's interesting. So about heavy stars, there is also a question. And how long is the lifetime of the 250 solar mass star? The question is from Awesome Quantum.
I'm actually not quite sure, but let's go back to that image. So you can see that timeline is actually exponentially decaying. So it's short. That's the short version. It's not more than a couple of million years.
Yeah.
But I'm not sure if we can run models of stars that are that big. So there are some these are all computational values. So we can't follow a star for 3 million years to actually see how old does it get. And I think there are some limits actually at the moment for how massive a star we can model computationally. So it's a good question.
But are there also limits of how heavy a star can form not also in the model, but in nature in general? Aren't
Yeah.
there also limits?
Yeah, they are. So it's hard. The thing that sort of combats gravity is the radiation produced by the star in the center, and it's really hard to become more massive than a couple of hundreds. But we actually, when we look back in time, we know that the stars were more massive than the ones that we see today, or we have models that predict that they were. We just can't figure out how to model them. In model that is model their interior. We can model that they should be there. We just can't model their interior.
Mm-hmm. Okay. So we have actually even more questions now. Yeah. So next one is what happens to a planet between two binary stars? And question is from Denisa Risa.
Sorry, can you say it again?
What happens to a planet between two binary stars?
Between two binary stars. So it can move around, but actually, as soon as you have a third body, which is what the planet would be a third thing moving around, the system becomes chaotic. So we don't expect that it could move around infinitely, but there are some setups where this planet could move around within these two in like a figure 8. That's possible. What's more likely for a planet to survive, though, would be if it was moving around far outside. That's the most stable system for this setup. That would be kind of cool, a bit like the Star Wars Tatooine planet, I believe. It moves around this double star system. So, and that is possible, and we have seen planets like that are moving around binary stars.
But but the systems where the planet is in between, they are likely to be not stable,
yes.
Right?
Yeah, they're not likely to be very stable. We expect that it will collide with one of the stars at some point and be eaten.
Okay, so next question is from Peter Darling, and yeah, so not a binary system, but if Betelgeuse explodes, is it likely to evolve to a neutron star or a black hole?
It should be a black hole. It's so big, I believe. But we don't. Okay, so actually, I said 20 solar masses hardcore. It's not hardcore. It depends a lot on, again, the age that the star was born in. Because we have this thing that's called metal enrichment of the universe, which happens slowly. And basically that means that more and more of these heavier elements than helium and hydrogen are present everywhere in the universe. And they actually make this mass of the star that is able to form a black hole decrease. So the more metal rich the stars are, that is, the later they're formed in the universe, the bigger they would have to be to form a black hole rather than a neutron star. So that was a very mixed question, but I believe that Betelgeuse should be a black hole. Yes.
Mm-hmm. So, and we have two more questions for now, at least, and those are, yeah, So one question, I think, yeah. So, would you expect the black holes in a binary system to eventually collide, and what would happen? The question is from Ulfa Aren Bjarnar.
I think you should stick around to the next talk.
Yeah. Okay, and the last question for now is: how big does a star need to be to become a black hole in comparison with our sun? The question is from.
Yeah.
Oh Jesus, Futrus.
That's okay. So like roughly 20 times bigger than our sun.
Yeah.
Roughly, around 20.
Yeah, which was covered already. Yeah, so we don't have any more questions for now.
Okay, so I guess we can thank Sophie again. Hopefully you're clapping from your home. So thank you, Sophie. I guess you can stop sharing screen now. We're a bit ahead of time. That's okay, because we have brought back a quiz. Do we want to take a 5-minute break now or go straight into the quiz? How do you feel? I guess it's up to Nikki. Oh. We do have one more question, actually. We have one more question for Sophie. We can ask that to you right now, and then I guess we'll go into the quiz.
How and why would a binary star system be formed instead of a normal star system?
Yes. So actually, when a cloud normally collapses, so stars are formed from these giant molecular clouds that starts cooling down and collapsing. But at the same time, these clouds, when they're far apart, they're rotating a little bit. But then, when you have a figure skater, she starts out with her arms far apart, and then she pulls her arms in and she rotates faster. The same thing happens with the molecular cloud. As it's collapsing, it starts rotating faster and faster because it's conserving its sort of rotational speed or rotational energy. So this angular momentum, I call it. And some of these molecular clouds, when they're big enough to form these really big stars, that also means that the angular momentum it has is really big. So instead of just being able to collapsing into one thing, it fragments on the way down, and you form multiple stars, or like at least two, right? If it's depending on how much angular momentum or how fast it's rotating in the beginning, you can split into two cores. But it's a very fun thing to YouTube Google, star formation of multiple star systems. It looks really cool if you want. I can recommend that.
Okay, thank you. We're getting a lot of demand for the quiz. So I guess, Nikki, do you want to take over and tell everyone about how the quiz is going to work and what the prize is and how the winners tell us that they won?
Yes, exactly. Okay, so let's start the quiz. It's with Kahoot, so everyone can join on their mobile phones or on their computer.
Do you need to share your screen?
Yes, I'm just gonna share my screen, and then we will have the code which you can enter. Okay, do you see my screen?
Mm-hmm. So, Nikki, there's a little bit of lag.
Yeah, it's fine. We can just wait some time. So here you can see the code for Kahoot. If you go to kahoot.it, I will turn off the sound. It's a bit annoying. Then you can enter this code and you will be joining in the quiz room. So now we're just waiting for players. We can just give it some time. Figure out your favorite nickname, and then we will see you all pop up here. I'm just thinking that the lag might be a bit inconvenient with the quiz.
Yes, sorry, I totally forgot about the lag that YouTube does. But they can read the question. Can they read the questions on their mobiles? I guess they can't.
No, actually.
Oh, okay.
Um,
I apologize. Let's see if I can turn off this lag. I don't know if I can. Stream latency.
Oh,
no.
cool. We have lots of people coming in.
Okay.
Yeah, but it's actually going to be a problem, I think, if they're not answering on time.
Oh, okay. How long would it take to update the answering time?
Yeah, I can do that.
Okay. I guess maybe we'll take a short break. About how long do you think it'll take? 10 minutes?
Yeah, it can be 5 minutes.
5 minutes. Okay. We apologize for this technical difficulty. We might take a break for 5 minutes and then get back to you with the Kahoot quiz. So we'll see you soon. Also, by the way, if you are enjoying Astronomy Untapped series and you would like to contribute, help us out, feel free to mobile pay us some donation money, which goes towards advertising and our admin tools that we use for managing the stream and our ticketing system for the live events, and which also help us get prizes for the quiz winners and maybe even gifts for speakers that we really want to have come along. So yeah, just keep tuned in and I'll let you know when the quiz is resuming. Okay, so apparently the quiz is ready to go. So I will bring our Zoom back on. There we go. Nikki, yes. So are we ready to start the quiz?
Hold on.
Sorry, that's okay. Is the pin the same, or is it going to generate a new pin?
Yeah, that's actually a question.
Nice.
So we might have to log in again.
It's okay. I'm sure we can be patient. We have a few other things in the chat. Okay. How do you make those awesome backgrounds? Well, on Zoom, you can set your own background and you can find high resolution images if you want. Zoom has some of them by themselves. This one that I took is actually from a holiday that I took to Svalbard, and I saw the aurora. So that was very fun, and I'm sure Nikki found her background somewhere cool online. So yes, you can just Google high resolution space images and you'll find some neat stuff that you can just have as your backgrounds.
Yeah, mine was actually a standard one, which is perfect if you have work meetings and you don't want to show your house in the background if you didn't tidy up.
Yeah. It's an interesting world we live in.
Yeah. Okay, it's done editing, so now let's see if we can still play with the same pin.
So you may share screen whenever you're ready. Thank you for being patient.
Yes, we did not consider this lag.
Yeah, that's on me.
Okay, I think we will have to start over. So yes, apologies, you will have to type in your nickname again. I will share the screen now. Okay, so yes, same like before, we have a different pin now and it should be fixed with a lag. So type in your nickname and then we are waiting for players. And just to go over this again, so first we will have some general astronomy questions, then some questions about gravitational waves, and finally some specific questions about Sophie's talk. And the winner this time, if you win the quiz, please take a screenshot and send it to us. So then we will give you tickets for the first real life event of Astronomy on Tap, which of course we don't know when it is, but we hope it will be soon. Okay, I hope you're quickly joining because it's already counting down. Yes, awesome. Okay, I see lots of cool names. Yes, and also with these free tickets, well, of course they're always free, but you know, guaranteed tickets, we'll also get some free drinks. So it will be a good prize. Okay, it's counting down now. 8, 7. Anyone wants to join? Yeah. Okay, nice. We have more people coming in. And I don't know if you know Kahoot, but it's also on time. So there are questions, and on your phone you will see the answers, which corresponds to things on my screen. But it also measures how quickly you answer. So if you know the answer, don't waste any time, so you get more points. Okay, I just see 1 star. That's really cool. We have a lot of players. This is gonna be good. Okay, if no more players are joining, then we are starting with the first question, which, by the way, the first question is sort of a test, just to see if it's working for everyone. So this will not actually be a difficult question. Yes, so warm-up question. What is your favorite pizza? And any choice is going to be fine, obviously. We just want you to test out how it works. There's no judgment about your taste in pizzas. Yes, okay, everyone's voting on their favorite type of pizza. That's cool. So you see how it works now. You can read the answers on the screen, and then you just click the corresponding symbols on your phone. And I guess it's waiting for everyone to answer. So if you haven't already, please pick your pizza. I'm not sure. No, it should actually move on when everyone answers. Yeah, so it might be that not everyone's answering, and then we have to wait for the complete countdown. But the other questions are not as long. I just wanted to make sure that the first one is working. Oh, okay, nice. So everyone answered. Pineapple was not so popular. And then we are moving on after this round with the serious questions. So first part is general astronomy. And here we have the first question. Places in the solar system where you can find cold H2O ice for your beer. Yes, multiple answers. So is it Titan, Saturn's moon, or the Earth's moon, or Mars, or do you like your beer warm? And just like before, please answer so then the question moves along if everyone put in the answer. Yeah, it's true. So if people are asking about if they missed a question, they also count the slides as questions. So there was just an in-between slide, which was slide number 2. So don't worry, you didn't miss anything. We're getting lots of answers now. And remember, timing matters for the points. Time is almost out as well. It's counting down here. 7, 6, 5. There's a little bit of lag, so you might think that you still have more time. Okay, nice. Yes, so the moon and Mars were the correct answers. I like my beer warm was not accepted. I'm sorry. And we have the scoreboard where you can see how you're doing. Next question, where is the Nordic Optical Telescope located? So is it in Greenland, Hawaii, Chile, or Canary Islands? Do they want the music? Oh, I mean, we can. I guess it adds some sort of tension, this music. Actually, I'm just thinking now that the music is in my headphones, so. Yeah. Yeah, apologies. Music will be for next time. We'll take it slowly for now. And it's counting down now already. 6, 5, 4. So this is real time, so please answer quickly. Okay, and it's done. So correct answer was the Canary Islands. And we can see the scoreboard updating here. Next question is just a true or false question. So in the asteroid belt, there are more rocks than the entire mass of the moon. Is it true or false? This is a difficult one. I also didn't know it. And I guess actually there's only 21 players left. Oh, 22. Okay, and the correct answer was, it was false. So that was a pretty equal division in answers. It was a difficult one. And then we're moving on to the second part of the quiz, which will be about gravitational waves. So first question is, who first predicted the existence of gravitational waves? Hope you can recognize the cartoon answers. Ah, okay, you're only seeing it now. That's a good indication. Okay, 10 more seconds if you want to answer. And done. Yes, so the correct answer was Einstein. And okay, so we're changing now. Case is now the first one on top. So it's getting exciting. Yes, okay, next question is, by how much does the distance between LIGO's arm change when a gravitational wave passes by? So if you can see the answers, first on top you see a photo of LIGO's arms, they're pretty big, and then how sensitive is it to measure the distance between the arms when a gravitational wave passes by? It's all pretty incredible. Yeah, Richie, if you can tell me when they're seeing the question and the answer, then I can read it. That might be nice. Yeah. Okay, 7, 6, 5. So hurry up if you still need to answer. And done. Okay, yes, the correct one was 10 to the minus 18 meters, so diameter of an electron approximately, which is pretty amazing, right? That we can measure such small changes. Okay, so moving on to the next question. What causes a kilonova? So you can pick from between different events. We have a black hole merger, a pulsar, which is a spinning neutron star, or neutron star merger, or a neutron star black hole merger. Okay, 10 seconds left to answer. And done. Okay, so it was neutron star, and a neutron star black hole merger. So pretty much any event that emits gravitational waves, but also because it's a merger of a neutron star, not just a black hole, also emits electromagnetic radiation, which is really cool because then you can observe this event with gravitational waves and with normal light. And so far we've actually detected one, if I'm correct. So this was a very special event. So the question is, what was not observed after the kilonova event, JW1700817? We always have amazing names. Okay, Alejandro can probably say more, but I think it was the first and sort of only one that we detected gravitational waves from, but also lots of other radiation. So please type your answer what we did not observe after this kilonova event. Because we observed pretty much almost everything you can observe in astronomy, but there was one thing that was missing. So 15 seconds left to type your answer. Will be nice to see what people come up with. 5 seconds left. Come on, guys. Oh, okay. I don't think everyone did something. Yeah, okay, we had 2 correct ones. Nice. Neutrinos, exactly. So we had all sorts of radiation that was observed, X-ray, optical, radio, everything, but and of course gravitational waves, but no neutrinos. Which was probably, we think they were still emitted, but just due to the inclination angle that we couldn't see them. Okay, M31 has an answer streak of 6 and is on top now, so that's pretty good. Then we are moving on to part 3 about binary stars inspired by Sophie's talk. And the first question is, why does a star become a giant star towards the end of its life? The answers are, it ate too much ice cream, or it ate another star, or its outer layer started boiling, or it had a bad allergic reaction. So let's see how well you paid attention to the talk. Yes, okay, most people got this correct. Well done. Okay, next question. How many times bigger than our sun are stars that can form black holes? And again, this is a question where you can type your answer. So just type a number of how many times the mass of our sun the star needs to be to form black holes. So not in letters, but in digits, just to be sure. "15 seconds left. "5 seconds. Nice. Yeah, 4 of you got it correct. Well done. M31 still on top, but CNA is getting close. Next question is, what is a stellar envelope? And actually now I'm realizing that I keep saying how many seconds you have left, but of course there's also a lag with that. So try to just answer as quickly as you can to be sure that you won't get cut off. So for this one, we have the options, either a clump of stars or an express postal service, the remains of a dead star, or the outer layers of gas around the star's core. Yes, well done. Most of you got it correct. And then we are on for the last question. So remember, if you win, take a screenshot and send it to us. So then we can award you with the prize. So this question is, which stars have the shortest lives? Options are really big stars, medium stars, really small stars, or all stars live equally long. Yes, okay, most of you got it. Really big stars, that's true. Short and violent lives. Okay, so we have the winner, which is M31. So M31, please take a screenshot of your phone and send it to us. And then we will reward you with tickets for the next event and some free beer.
Yep, so you can, I guess, either message us on Facebook or Instagram or I guess Twitter, which I barely use, or our Gmail, which is aotcopenhagen@gmail.com. The screenshot.
Yes, we are everywhere. You can find us.
Yeah. Okay, I guess we're running into the time for Alejandro's talk, so should we just go straight into that, or do we want to take a little break?
I guess maybe people need to go to the toilet, get some drinks.
Yeah. So how about we just take a 5-minute break and we will resume with the second talk, which is about gravitational waves. So we'll see everyone soon.
Thanks for joining with the quiz, everyone. We'll make sure that it goes a bit more smoother next time. We didn't really take the lag into account, but we're still learning, and we hope you enjoyed it nonetheless.
Okay, I hope that everyone is refreshed and had a little break. So we will continue on with the second talk for tonight. We just learned about how we can get these binary black holes together and that they can eventually get close enough and maybe smash into each other. So Dr. Alejandro Vigna-Gomez will tell us then about these actual events of black holes smashing together. So Alejandro, would you like to take it away?
Yes, thank you. I will do the usual sending of the slides and stuff. Please let me know if you can see my cursor on the slides.
I can see your cursor.
Fantastic. Well, thanks for organizing these. Today we'll be talking about the moment when a binary black hole forms, and then what happens afterwards. So Sophie already told us what happens from stellar formation to binary black hole formation, and then the point now is to try to understand a little bit of the rest of it and the detections of them in gravitational wave sources. So there's some questions that I will not answer this time. So what is inside a black hole? Spoiler alert, no one knows. What happens if I fall inside a black hole? Well, people claim about spaghettification, but I also don't know. What is a wormhole? What about time travel? And what should I do with my life? So with this disclaimer, we'll go on to gravitational waves, and particularly I want to point out on a historical note, the Hulse-Taylor binary. So this is a binary neutron star. After this slide, we will only focus on binary black holes, but there is this binary that was initially detected in 1975, and then they followed throughout decades until 2005, when they finally published a study about what happens to the orbit, or particularly the separation of this binary throughout decades, and this was the first indirect detection of gravitational waves. So this was detected as a radio pulsar, which means that one of the stars is a neutron star that is emitting pulses. The other companion is also, it was a neutron star. It was defined as a neutron star after some observations, but the point is that if you follow the evolution throughout the decades, you can see that the separation diminishes, and this is a direct effect of gravitational waves, and therefore it was the first indirection in 2005. But of course, 10 years later, gravitational waves from a binary black hole coalescence were measured. So first thing first, what are black holes? The point with black holes is that they are regions of space-time that effectively do not allow for the exit of light or other sources of energy. And something important to remember is that you have, for example, the mass of the sun that has today a radius of around 1 million kilometers. And if you compare the same mass, but if it's in a black hole, the radius is of around 1 kilometer. So you have that a black hole has an effective radius that is 1 million times smaller than the one for the sun for the same mass. A thing that we should remember is that the sun is not massive enough to form a black hole. So this is more like a thought experiment. But the size and the mass of it could be of this size if there was, for example, things called primordial black holes, which are black holes that are not formed from stars, but that they were formed early after the Big Bang, or at least early after inflation. A black hole, especially if it's non-rotating, which are the easy ones, and that's the ones that I want to discuss more. They are defined by a singularity in the center. A singularity is a point of a very, very high density. Some people would claim that it has an infinite density. Some people would claim that it's not infinite, but it's still very high. And that has an effective radius that is called the event horizon. After, well, if you enter that region, you will not be able to transport information outside. And with information, for example, we could mean light or other sources of energy, which are what we usually use when we try to understand stars or just the astronomical events. So Sophie already told us how stars become binary black holes. And what I just wanted to remember from this plot is that we care about what happens after everything has happened, and when we have the two pairs that are in the bottom of this plot. Now, when we have them, what happens is that we start getting gravitational wave emission. So here in the big panel on the left, we have what is sort of like a grid trying to portray space-time, and we can see that space-time is distortion depending on the mass and the size of the object. In this case, we can see that the one that it distorts more, that bends it, is the yellow, more massive system. But it's not necessarily about the size, it's also about the density. So it could be that, for example, another ball that was maybe not that big, but denser could distort this equally or more. And when this happens, and when a pair of these balls are in a binary black hole, there starts to be this emission of gravitational waves that looks a little bit like ripples in a pond. So actually, when I look for ripples in a pond, which is what I wanted to show, the first thing that bumped up in Google was an article about gravitational waves. So I think this metaphor is now kind of in the mainstream. And if you go in the panel that I'm signaling in the top right, you can see that there's kind of like an emission in the center, and the further out you go, the more you can see that the structure of the gravitational wave emission looks like when you throw a stone or something into a pond, and then it just emits, well, in this case, the waves in the water that in this case are analogous or looks analogous to gravitational waves. So now we begin with some of the hopefully cool videos. Let's see. There we go. And what I wanted to show here, here is showing the first gravitational wave event, GW on 150914. GW stands for gravitational waves. And then 150914, 15 is the year, 09 is the month, and 14 is the day. So it is not as difficult as it sounds, and that's how the nomenclature of each of the binary black hole mergers is referred to. And here there are two plots effectively. The big one, the pretty one, has the evolution of the two black holes that are getting closer because they're emitting energy via gravitational waves. When you lose energy, you get closer and closer and closer. And in the bottom, if you follow, there's a wave that we will analyze a little bit more in detail later. But I wanted to show that at the beginning, this wave is kind of like oscillating, and then it starts oscillating faster and faster. And this has to do because the binary black holes are getting closer. Now, at this point, you get to the moment where the event horizons will start touching. And this is effectively where the merger occurs. Then now we have that it freezes. This is the most complex part of the merger, because afterwards you go from having two black holes to having a single black hole, and that's where most of the emission and gravitational waves occurs. As you can see here, the emission is ongoing and then it stops. Oops. Now, how do we detect these things, or what's the point of this? We effectively use gravitational wave observatories, the first one being LIGO, Laser Interferometer Gravitational Wave Observatory. And what LIGO does is uses light. Light has this very nice property that it travels at the speed of light, which is effectively, especially in very isolated environments, it's a constant velocity. So what we do is we have two arms that are perpendicular to each other, and we're measuring the travel time from each of the arms. So you have like an L, and then when you're measuring the travel time, it should remain fixed if nothing happens in both ways. But if there's a distortion that happens on one way, then you get an interference pattern, and that is when it's telling you that there's something weird from one side and maybe not the other, and that it could be related to a gravitational wave. Of course, it can also be correlated to an earthquake or someone banging the detector. But the point of LIGO is isolate all of these sources of noise that are not actually gravitational waves, so that at the end of the day, you can see only the effect of gravitational waves on the travel of each of the arms. So at the beginning, with the first observation, there were only 2 detectors, LIGO, Hanford, and Livingston. But there's now also Virgo has been integrated, and there's the plan that Kagra and LIGO India will join. And this is important because the more detectors you have, the more confident you can be on your detections, the more confident you can be in cross-referencing information from one detector. For example, if 2 of them are seeing very similar things and the other one isn't, why is that happening? What does this tell us about the astronomical source? This doesn't mean that it's wrong or anything. It just means that you get, with more information, the better it is to, with more detectors, the better it is to have more information. So then you can make inference about, for example, the masses of the black holes, the spins, which means how fast are they rotating and in which direction, and things like that, their eccentricity, etc. So here's an exaggerated effect of a gravitational wave passing through Earth. And the point is that you can see how it wobbles the Earth. And this is effectively what you want to measure with your gravitational wave detectors. Once you see this, then you can see that in one direction it wobbles more than in another. And that's how you can start making the inference. But what are gravitational waves and what are the waveforms? Because this is very important. So if we go to the panel on the left, we can see that we have like time, and then effectively we have the wave that is traveling through time. And this wave corresponds to the 3 main phases of a binary black hole merger. So we have the inspiral, which is when the 2 black holes are kind of far, but getting slowly closer and closer and closer. Then we have the merger, when the event horizon touches, and then effectively 2 become 1. And then the ring down, which is after the merger, you still have some final perturbations. The black hole is trying to get to a stage where it's in a relaxed steady state solution. So that's like the final phase. And you can see that through the waveform, because at the beginning, it's kind of similar, oscillating. Then it starts getting faster and faster, the closer and closer it gets. Then you get the peak of gravitational wave emissions at the moment of the merger. And that after the relaxations, there's still some oscillations, but the amplitude, which is just effectively the size of this wave, is significantly smaller. And at the end, it becomes, it no longer oscillates, and it's just a steady state solution of a single black hole. I also wanted to point out that what LIGO actually uses is waveforms, which it means that they run numerical simulations of these binary black hole mergers. They construct what are called templates of these signals, and this is what they cross-reference to when there is a signal. In this way, when they measure anything, they go to a bank of these templates, they see, hey, does it match? And if it does, then they can start talking about a detection. If not, then it's probably noise, or maybe something weird that needs to be taken into consideration separately. And this plot is from the first time that Franz Pretorius in 2005 in Princeton managed to model the simulation of the merger, because the first part, the spiral, is very easy to model because things are kind of far, so you just use approximations. But the moment when the 2 black holes touch, that was an open problem in physics for decades, until Pretorius finally gave us the answer. This is the plot, so this is the waveform. And following this great piece of work, there were many other people that were replicating this, and that's how the templates of this gravitational wave evolution were formed and were put into a database that then later was used by LIGO to see if the detections were actually coming from a binary black hole merger. However, real signals are not as pretty as the ones we saw before. I'm gonna go back just to see. You can see here that this is very pretty. Even this one from Pretorius is kind of like smooth and cool. But when you get the real stuff, which is again the spiral, the merger, the ring down, you can see that there's a lot of wiggles, that they're not nice and stuff. And this is one of the main problems with LIGO, or the important things to be taken into account. And that's why the coincident detection is so important. So here you have on the top and in the middle, two different detections that actually happened slightly on different times, because of course, as the observatories are in different places, it arrives the gravitational wave front first to one observatory and then to the next one. And then you need to see if this offset in time, how does it look, and then if they're actually the same as it looks here in the plot on the bottom, then you can claim that there's a confident detection, because it is not necessarily that it will be the case. So this is when, with real signals, with added noise and with a lot of wiggles and stuff, when the multiple detector thing becomes more important. And this sky localization, it's also quite a big deal, especially for trying to see if there was any other emission on light that was not gravitational waves, for example, X-ray or gamma ray emission. And the comparison here is what's the difference between having the two LIGO observatories, which is in the blue patch region of the sky, against having three LIGO observatories, in this case adding the two of the LIGO and Virgo. The difference here is that, as you can see, when you add the third observatory, then you can constrain better the size or the sky area where you can look for. And this is very helpful, because when you point out telescopes there, then it's easier to look in a smaller area than in a larger one. The problem is that actually both LIGO detectors have a similar sensitivity, but Virgo has a less sensitivity. So Virgo only can detect binary black holes that are relatively nearby, and therefore sometimes even there are non-detections from Virgo that are detections for LIGO. And again, this is not necessarily bad. This is meaning that also gives you information about where could this be. But the comparison that people make is that, for example, you have like the two very good LIGO detectors, then you can realize where things are, because they're in this region when they're maybe close, but the sky area is quite big. But if you have the three detectors with different sensitivities, then you can see that the sky area is very small, but the inference of the distance, so how far they are, becomes a little bit more difficult. So it's kind of like one of these things that probably it's easier to have more detectors to see how small is the sky localization, but to make inference about the distance and therefore the cosmological properties of the signal, it might become a little bit more difficult. But on the other hand, if you didn't have the detector, you wouldn't be able to see that far. So these are the masses in the star graveyard, and this is just to point out that actually there's a lot of systems detected now. In 2015, we detected a binary black hole merger for the first time. Then after that, there's been like different set of detections, different observations called LIGO observation 1, observation 2, and observation 3, and they've been adding binary black hole mergers. And this is the up-to-date presentation of these binary black hole mergers. Again, I'm not showing here the couple of binary neutron stars that have been detected or the potential black hole neutron star system that is there, but it's just the binary black holes. Nevertheless, they're the most, because binary black holes are heavier than binary neutron stars or black hole neutron star mergers, and therefore the heavier they are, the more likely they are to be detected, and the further away they can be detected. So this is just to remind ourselves that this is already happening. We have tons of detections, and that they will keep growing, and we will be able to do statistics on these systems to understand the properties of the populations in the future. And one last piece of conversation I wanted to discuss or to show is that there's a very nice effect that binary black holes have when they merge, and it's that they can get a remnant kick. So for those of you that maybe have studied physics or so, this is the same principle as a conservation of momentum. So you have two things that are spinning in maybe different directions, and then when they merge, they get a final kick. So the final black hole gets a velocity towards one direction. So here there are three examples. And then we will just show, you can see the evolution of the waveform in the bottom of each of these panels. And the most interesting ones, which will be, if I'm not mistaken, the ones in the left and right. I think that the one in the middle will not do anything because it's not spinning, but the one in the right and on the left, they might do. They will get a final kick that is called a gravitational wave recoil kick. And here it happened already for the first one, but it didn't. Okay, so let's wait until the other ones. And then this is just telling us that this is an effect that happens, that a binary black hole gets a velocity once it merges. Technically, the arrow is showing the effect of the spin and the kick. And well, that's it. So thanks everyone. I think I had an extra slide, but I'll just skip it for next time. Cheers.
Thank you, Alejandro. That was really good. We already have some questions in the chat. People were very keen to learn about black holes merging. So, Jörgi, do you want to take over?
Yeah, so we for now have two questions. And the first one is from Jürgen Skut. And the question is, shouldn't it be possible to detect gravitational waves in distortion of fast signals, like the carrier signal from distant space probes?
I'm not sure if I understand the question, but I'll answer something, and then if that's not what you were asking, then you can ask again, and then we can give it a go. But for example, what gravitational waves detectors are measuring is distortions of space-time, which are effectively distortions of very dense objects. So this is why binary black holes are very good to measure them, because there are two very dense objects that are merging. But another thing that could be is during the supernova, if it was close enough, the core of the exploding star, that can be a few thousand of kilometers, gets a lot of perturbation. So it loses the spherical symmetry, and this loss of the spherical symmetry, which you can imagine like a ball doing weird stuff, like kind of like the Earth that we saw in the presentation when the gravitational waves were passing. These deformations can emit gravitational waves that can be detected. So that's an example of something that we can see, that we can measure gravitational waves that are not binary black holes. And another example is for a neutron star that loses spherical symmetry, and again, that has, for example, two little mountains on top. When it's rotating, this loss of spherical symmetry gives you an emission of gravitational waves that again could be detected. I don't know what sort of probes were you referring to, but hopefully this gives you an idea, and if not, please refine whatever you wanted to know.
Could I chime in? I guess my interpretation of the question is, I guess there's the Voyager probes and stuff that are sending signals back to Earth regularly. Would those signals be affected by gravitational waves passing by them? And can we use that to know when a gravitational wave comes by?
Yeah. So that's interesting, because I don't think itself one of these probes sending signals would be able to do it, because the light that they're emitting is not distorted by gravity. But what there is that, sorry, it is distorted by gravity. It's not distorted by gravitational waves. But what could happen is that, for example, what people use is pulsars. So these are neutron stars that are just spinning in all regions of the universe. And therefore, there is something that is called a gravitational wave background, which is some sort of gravitational waves that have been emitting throughout all the age of the universe that are already there, like some of noise. And there's also things that they could be like some binary black hole mergers that are from galaxies, so supermassive binary black hole mergers. And when this happens, they will change the spinning of these pulsars, and therefore the signals that they send, they will actually be modified. So this is a thing called pulsar timing array, and this will serve like that. So if you were referring to, for example, pulsars as probes, yes, definitely. With things like other types of man-made probes, I don't think so, but yeah, I'll just stick with my answer with the neutron stars.
Okay, so next question is, so do gravitational waves experience normal wave effects like reflection, refraction, diffraction, or can they cancel each other, or can they superimpose on each other? I guess So okay. That doesn't happen to gravitational waves.
Yeah, that's a good question, and it's a very good question because I think my answer is yes, but I am actually not incredibly sure about which ones do or they do not. So I think superposition and all refraction, yes, they do happen. For example, that's the gravitational wave background that I was talking about, is effectively that. You have, let's say, two pairs of Albanian black hole merge, and then or maybe thousands of them, and this just creates kind of like a superposition of all of them. There's also experiments about maybe using the sun as a gravitational wave detector, when you can have like this, because it's close enough for us, and the mass that it has is big enough that it bends space-time, so maybe you can see some refraction of gravitational waves, and that is somewhat accepted. But I don't know at what point do the degeneracy, with degeneracy I mean, at what point do they stop being equal to mechanical waves the way that we know? So I guess my answer would be yes, if I had to bet, but I will owe you in which cases they don't.
So is it right? Did I understand right that such things happen for gravitational waves, but there are certain aspects in which they are different from what we learned, like in mechanics at high school or something, right? Like there are,
yes,
yeah.
That's what I think. Yes, but in most cases they are analogous.
Yeah. Okay, so we actually have more questions, and so the question is, can gravitational waves be like rotations or other things, or are they always waves? I'm not sure I understand it, but I'm not a physicist.
Maybe let's see if this makes sense. So black holes can be rotating, and the effect of the rotation will have an effect on how do they emit gravitational waves. So depending on, and for example, how fast they are rotating, depending on which direction they're rotating, this will emit more efficiently or less efficiently gravitational waves. And therefore, this is something that actually, when a gravitational wave event is measured, this is the information that we try to take from. Like we try to say, okay, was the progenitor rapidly spinning? What was the direction of the spins, and these kind of things? So rotation certainly plays a role in gravitational wave emission. I don't think that you can. Yeah, I'll just, I think that's the way to explain it.
Okay, thank you. Yeah, I think yeah. But just in case, feel free, everybody in the chat, feel free to specify your question if you feel like some even minor aspect was left out or something like that. Oh, yeah. So there is a continuation to this question, and says, but can the fabric of space-time be twisted?
Well, so this was in my disclaimer slide, when apparently the twisting of the fabric of space-time can lead to these wormholes, for example, and then it can that's even when they tear the fabric of space-time. So I guess there are theoretical ways of describing this breaking of the fabric of space-time, and maybe doing some trajectories or geometries or topologies of spacetime that get you to some exotic configurations. But for the principles of astronomers, which are people like us trying to understand space, this is not at least until now, it is not straightforward to know what would be the effect and how could we measure the effect of such extreme distortions of space-time.
Okay, yeah. So now I understand the question. But it's very difficult. Okay, I think we have one more question. So next, not one more questions, but next one is, how are gravitational waves affected by inflation?
Ooh, how are gravitational waves affected by inflation? I don't know. I don't think I've ever thought of that. I don't know, Nikki, maybe you are a little bit more of a cosmologist. I don't want to put you on the spot, but I
mean, they probably gonna be redshifted, right? As well.
Well, would they be redshifted or would it just be stretched?
I don't know, but
so
I guess, if you have gravitational waves from black holes, for example, they were not around when inflation happened, right? So I don't think that the gravitational waves that are sent out now will be affected by inflation, but I did hear there were some theories predicting gravitational waves from the very early universe that you can measure, which were not from black holes, but maybe from inflation or some processes there. But yes, I don't know.
Yeah, so what Nikki says is it's very important, because most of the black holes that we know today are formed because of stars. So we don't expect them to be during inflation, but there are things like primordial black holes that might or might not have been before or during inflations. And also there might be some gravitational wave emission from the early anisotropy of the right after the Big Bang, that everything was just that's pretty dense, right? And you have maybe some anisotropy that emit gravitational waves. Yeah, I'm sorry, that's a great question, but I don't know the answer.
So I might chime in again. I'm not sure if they mean inflation as astronomers mean it, but maybe they mean just the expansion of the universe. Do the gravitational waves get affected by the expansion of the universe?
Yes, they do. Okay. So in that case, then they get redshifted, and then the further away they are, the more of the redshifting happens. So I think maybe that's the way to think about it.
Okay, thank you. So we have more questions.
I think just one more related to this talk. It's from Nicholas.
No, this particular one. No, the question is not from Nicholas. The question is from Claudia, and the question is, how close does the source of the gravitational waves need to be for the Ligo to be able to detect it?
Okay, I think close, we would detect anything that it's, let's say, we know there's no tiny black holes in the star, like supernova.
I apologize. We're having some.
I think the question.
Both of you are quite robotic. So we'll see.
Okay.
It might be affecting the stream.
That's okay. Now you seem to be back. Do you want to repeat what you just said? We apologize.
Okay. So go on.
Yeah. So I think the question is vice versa, in a sense that how far the things should be that we will not see it.
Yes.
Yeah, like of course, if the closer it is, the easier it is to see.
Yeah. I just want to make them clear. So the Ligo. So what people usually reference is the how can be the star or the Vigo Observatory. Stars are the most lightest actually detect. If you are, the easy to detect because less sensitive detector.
I am very sorry. You're coming through now, but you were lagging and becoming robotic again. Yes, so I'm not sure what's going on. I guess the internet is being busy, got a lot of bandwidth. But I guess yes. We could try one more time. Wait, can you speak right now? You seem to be lagging a little bit.
I can try to speak and see if we get rid of the robotic. Maybe I just speak like a robot and you haven't noticed.
I think it's a YouTube problem because so yeah, like YouTube works badly right now.
Okay.
I can't watch stream right now online.
Well, okay,
like,
if that's
before
that,
before I was two screens and it was fine.
we might wrap it up because we've gone over time, and I guess if we're having technical difficulties, we probably don't want to make everyone suffer. We're super sorry, but we did have really good discussion and really good questions, so we might just get everyone back and thanks Sophie, thanks Alejandro, thanks Nikki and Jurgi for having another Astronomy on Tap online. Hopefully we can see everyone at the next Astronomy on Tap. Right now with the restrictions, it's planned to be in person, but they might be extended. Next month's Astronomy on Tap, we're working together with Kfine Physics to just bring together two amazing astronomers to talk about ghostly neutrinos, which I guess Sophie briefly mentioned, and Anja Andersen, who is a pretty famous Danish science communicator. So please follow us, and we'll thank Sophie and Alejandro and our helpers again. So thank you again.
Thank you.
Okay. Take care, everyone.
Okay.